Hello and welcome back to EGR 151 Electrical Machinery. In this unit, number 19, we're going to be looking at capacitors. As usual, I recommend you read your text or at least review it before you do this presentation. So, what are we trying to accomplish in this unit? Well, we want to study the various factors that affect a capacitor's capacitance. We need to understand what an electrostatic charge is. There are two types of capacitors, non-polarized and polarized. We need to know the difference between those two. We need to determine the various electrical values associated with capacitors connected in series and in parallel. And lastly, we want to calculate what's referred to as the RC time constant. It's actually very similar to the time constant that we spoke about in inductors, but it deals with capacitors. So what do capacitors do? Well, the fact is capacitors are able to store charge. So as a result, we can do a few different things with them. For example, if we want to correct our power factor for a certain application, if you recall, power factor related the apparent power to the real power. If you want to change that, you can use capacitors to do that. They also store power when we want to use it for creating sudden bursts of high levels of current. We can also control the timing of various devices, and then we have them for filters, essentially clean up different power signals. These can be polarized or non-polarized. In general, non-polarized ones can be used for just about any type of circuit we want, AC or DC. Polarized are going to be limited to DC circuits only. So capacitors actually oppose any change in the voltage, and they do it with this layout that we see below. Turns out they're made up of two plates, right? And the size of the plate is an important factor, and they're separated by a material known as the dielectric. Dielectric is essentially an insulative material, and it prevents direct flow of current across these two plates. And depending upon the dielectric, it'll tell how much eventual current we can force through it. And that only basically occurs when we're charging the capacitor or discharging the capacitor. So the way capacitors work is, as I said, we have these two plates. When we put our charge on here, right, it will push electrons to one side or the other. In terms of how much electrons it can push, well, it depends on how big the plates are, essentially the surface area, how wide they are separated in terms of the distance, and then, of course, the material making up the dielectric, right? And keep in mind, this is a simplified diagram. In terms of the actual layout of the plates, there might be multiple plates involved. The plates don't necessarily have to be flat, so there's a whole variety of different constructions out there, but they all have the same basic features of plates separated by a dielectric material. So when you first connect a capacitor in a circuit, you're going to get a flow of electrons, flow of current, until the voltage across the capacitor is the same as the applied voltage. And at that point, the current flow is going to stop. Now, if you disconnect the battery or power supply, it turns out that that charge remains. So essentially, you have now stored electrical power in this capacitor for some other application. So you may be asking, how does current flow across material that is considered insulative? Well, the reality is our dielectric material can be a very good insulator, but it's not a perfect insulator. So when there's a voltage on it, you're going to get a certain amount of electron flow from one side to the other. And when you disconnect it, you're actually going to get a certain amount of electrons leaking back through the dielectric, and over time, capacitors will actually lose their charge. Now, keep in mind, in terms of the overall storage of charge, this is being done by what's referred to as an electrostatic charge, right? So we think of them as static, and it should be relatively static. And the other thing that happens is what's referred to as dielectric stress. So let's take a look at what's happening with the atoms in the dielectric material. So when a capacitor is not charged, we're going to find that our atomic structure is relatively symmetric. So you're going to get essentially round or spherical atoms, and the electrons are going to be essentially evenly spaced around here. On the other hand, once we put a charge on the capacitor, not only have we moved electrons, but we've also put what's referred to as a dielectric stress on the individual atoms making up the dielectric. And what we see is the electrons in the actual atom are going to be pulled toward the positive side, away from the negative side. And essentially, they're going to stretch the atoms like a spring. Right? So we're storing our charge in two forms. One, the form of this electrostatic charge of moved electrons, and the other one in these stretched or distorted atoms. When the capacitor is discharged, all this essentially comes back to this original format over here. Different materials have different dielectrical constants. Right? If we take a look, air, for example, has a relatively low dielectric constant. On the other hand, if we look at better insulators like ceramics, they have a very high dielectric constant. And it turns out that different materials are going to give us different amounts. For example, pure water is relatively high, if you recall, right? Pure water does not allow current to flow very far. This actually has a dielectric constant of 81. So it turns out that different materials, depending on oftentimes on their electron configuration, are going to have different dielectric constants that we can use for calculating the capacitance of a capacitor that uses these various materials as the dielectric. So the basic unit for measuring capacitance is the farad. And it uses the symbol F. The way the farad is derived is based on the charge and the voltage across a capacitor. It turns out if you have a 1 farad capacitor, use the symbol C for capacitance, and it has 1 volt across it, then it's going to move 1 coulomb of charge. Charge uses the symbol Q. Right, so these three units are interrelated in that way. On the other hand, if you want to look at the physical makeup of a capacitor, it turns out that the capacitance, again, C in farads, is going to depend upon the dielectric constant. Right, so a higher dielectric constant is going to give you more charge. The area of the plates divided by 4.45 times D, where D is the distance between the two plates. Right, so bigger capacitors are going to have more charge. Greater distance is going to cause less charge. Now, we can connect capacitors up a couple different ways. If we connect them up in parallel, so in parallel, essentially we have multiple branches. Right? It turns out our total capacitance is just going to be the sum of all the capacitance shown in parallel. If you think about it, each of these are able to hold a certain amount of charge. As a result, when you put them across multiple paths, they can hold that much more charge. So in this case here, if you had a 20 microfarad capacitor, a 30 microfarad capacitor, and a 60 microfarad capacitor, these would just sum right up to a 110 microfarad capacitor. On the other hand, when we connect capacitors in series, right, where one after the other, they actually cannot increase the capacitance. They actually limit the capacitance between them. And in terms of the relationship for calculating, use that reciprocal relationship, similar to how we calculated resistors in parallel. So our total capacitance is going to be equal to the reciprocal of the sum of the reciprocals. So 1 over the sum of 1 over C1 plus 1 over C2 plus 1 over C3. So in the case we use those same three capacitors, now we have 20, 30, 60. Because we're adding these up in a reciprocal relationship, it turns out the total capacitance is only 10 microfarads, right? Less than even the smallest of the capacitors that are put in series. Now, it turns out that it takes some time for capacitors to essentially be charged and then discharged. And very similar to what we talked about with inductors, it follows an exponential curve, right? Similar to inductors again, we divide that curve into 5 time constants, and each of those time constants represents a change in about 2/3 of whatever the voltage that remains. So in the first time constants, you're going to change the charge by 63.2%. The next one, you're going to change it by 63.2% of what's left, 63.2% of what's left again and again and again. By the time you get done with the 5th time constant, it's close enough to the full voltage that we don't really have to worry about the fact that there's a small deviation there. If we look at our curve, as we start charging our capacitor in the first time constant, in this case, we're going to a total of 100 volts. We're at 63, then up to 86, then up to 95, 98, etc. So by the 5th time constant, we're pretty close to 100, or close enough for almost all applications. Similarly, when we discharge a capacitor, it discharges very quickly in the beginning. Again, about 2/3 of the way in the first time constant, then another 2/3 in the next time constant, etc., all the way out to 5 time constants, where it's considered fully discharged. To determine the time constant, you need to know the resistance R, this is going to be in ohms of the capacitor, and the capacitance in farads. You multiply those two together, R times C will give you the time constant tau. For time constants, we use the Greek letter tau, lowercase tau in this case, and this is going to be in seconds. In terms of these are represented, it's just going to look like a small capital T. Oftentimes it's going to be bolded to represent the fact that it's a symbol, but it doesn't have a very unique symbol as compared to some of our other Greek letters.